So today we are going to talk about torsion. So that is a very, very important loading state, very ubiquitous as well, similar to bending. And for torque, they act basically through a lever arm. And materials will experience similarly torsional stresses, torsional displacements, and we're going to do the geometric statement, constitutive equations, and equilibrium conditions again. So our geometric statement, similar to what we saw for bending, when material undergoes torsion, it's going to undergo some displacement delta that we can relate to that basically our arm or the radius and that d theta. Our constitutive equations, we can relate that displacement to a strain. So that initial delta there divided by dz, again, you can see that's kind of similar to that kind of shear type displacement. It's pure, basically this is a pure torsional state. And with those stresses and strains, we can develop our equilibrium expressions. So we could basically, we're looking at the sum of those moments on that differential area. We recognize once again our moment of inertia equation, and we could work to develop the expression below. And here it's important that t, j, and g are all constants in terms of z. And we finally get the expression for our stress. And it's very interesting because you can see that these torsional stresses are independent of the choice of material because our g has been removed from our expression. So we don't have essentially that shear modulus effectively here. So your torsional stresses are really geometrically, or these kind of constants, defined. So very, very similar to our thin wall pressure vessel analogy and experience. So you can do and derive similar expression from our energy considerations. We'll go ahead and skip that. Again, it's always nice when things match, but that is it for torsion.